Hello, I am Nirmala Morade, Assistant Professor, Mathematics Department from S.V.K.T College, Devali Camp, Nasik. In today's lecture, we are going to study the concept of linearly dependence and independence of vectors and some related examples. Now, first we will see what is meant by linearly dependent and independent vectors. So, for that we consider a vector space or some field. So, let V be a vector space, consider it some subset. So, suppose we take S is equals to a set containing some vectors from V. This is a subset of V. Then this set S is said to be linearly independent if no vector in S can be expressed as a linear combination of the others. Again, see the definition. The set S is linearly independent, or all these n vectors are linearly independent if no vector in S can be expressed as a linear combination of other vectors in S. If the set is not linearly independent, it is called the linearly dependent. So, these are two important concepts in linear algebra. Again, see the same definition. S is a vector space. S is a vector space. V is a vector space. Take S containing the vectors V1, V2, Vn. It's subset of V. This S is said to be linearly independent, or these vectors are said to be linearly independent if no vector in S can be expressed as a linear combination of other vectors in S. If set is not linearly independent, it is said to be linearly dependent. Now, let us see some examples related to it. So, now we consider the vector space R2 with the usual addition and multiplication, component wise addition and component scalar multiplication of elements in R2. So, let S is the set containing the standard unit vectors. So, first is 1, 0 and next is 0, 1. It is a subset of V, and we can easily check that in this set no vector can be expressed as a linear combination of the other. We can't express 1, 0 in terms of 0, 1, that is second vector, and the same for the first one. This is one example of with the set which is linearly independent. Now consider the another example. S1 is the set containing two vectors 1, 1, 2, 2. It is a subset of V, that is R2. So, you can easily observe here the one vector can be expressed in terms of the other. That is, I can write the first vector 1 1 as half times 2 2, or the vector 2 2 can be expressed as 2 times 1 1. That is, here one vector is expressed in terms of the other, and since there are only two vectors, so one is a scalar multiple of the other, that is, one is the linear combination of the other, and so this set is the set S1 is linearly dependent because it is not linearly independent. Okay, but now these are only two vectors in R2, so we can easily check whether they are linearly dependent or not. But if set containing more than two vectors, then how to check it? So for that we use one theorem. Now let us see the statement of that theorem. Now this is an important theorem related to linear dependence and independence. So we first consider S is the subset of vector space V with S having the elements V1, V2, Vn. This S is said to be linearly independent if and only if the equation alpha 1 V1 plus alpha 2 V2 up to alpha n Vn equals to 0. The left hand side of this equation is the linear combination of all the vectors in S. And we put this linear combination equals to 0, solve this linear equation. Actually it is a system, linear system, and if this system has trivial solution, that is all alphas are 0 here, then we say that the set is linearly independent. So obviously if set is not linearly independent, if this system has non-trivial solution, non-zero solution, it is also called as a zero solution. Zero solution means every value of each variable is equals to 0. Now we will solve the problems by using this theorem. So suppose we want to show that whether set is linearly dependent or not independent. In that case, first we consider this equation and find its solution. When we consider this equation, and after putting the values of these vectors v1, v2, vn, we will get one homogeneous linear system. We can solve this linear system by using either Gauss elimination or Gauss-Jordan method and find its solution, and depending on the solution, whether solution is trivial or not. If it is trivial solution, you can say that the set is linearly independent or vectors are linearly independent. And if system has infinitely many solutions, that is non-trivial solution, in that case we say that S is not linearly independent, that is it is linearly dependent. So now before going to solve the problem, we will see some important result, or we mention here some important results that are useful for solving such a type of problems. So for that we consider the non-homogeneous system. So we write this linear system, this is a homogeneous system, linear homogeneous system, and we know that this linear homogeneous system is always consistent, either it has a infinitely many solutions or trivial solution, that is only the zero solution. It is always consistent and it has a two types of solution. Trivial solution or non-trivial solution. Okay, trivial solution means the value of each variable is equals to 0, and non-trivial means at least this x not 0 means at least one value from this matrix is non-zero. So there is one result related to this. So this system Ax equals to 0 has trivial solution. You can also say that zero solution if and only if the determinant of coefficient matrix is not equals to 0. This is the important result while solving the problem. The homogeneous system Ax equals to 0 has trivial solution, that is zero solution if and only if the determinant of A naught equals to 0, and the second result is you can write here non-trivial solution, non-zero solution, that is it contains infinitely, it has infinitely many solutions if and only if determinant of A equals to 0. So these results are useful if there are number of equations in the system is equals to the number of variables. That is A should be a square matrix. At that time we can find the determinant. Otherwise, to find the solution of the system, either you can use the Gauss elimination method or Gauss-Jordan method. So now let us consider some problem. We consider R2. The set S is equals to containing two vectors 1 1, 1 0. Okay, now we check whether this set is linearly dependent or not, or it is linearly independent or not. Okay, so now for that we use the statement of the theorem. So for that we consider the equation whose left hand side is the linear combination of these two vectors and right hand side is the 0. That is, we consider here alpha times 1 1 plus beta times 1 0 equals to 0. This 0 indicates the 0 of the vector space, and the 0 of the vector space R2 is 0 0. Okay, now solve this equation. So now first use the scalar multiplication. So first this can be written as 1 times alpha plus this is same as beta 0, this is equals to 0 0. Add these two equations, these two vectors. So this is same as component wise addition and component wise scalar multiplication. So the first component of this addition is alpha plus beta, and second is alpha plus 0, that is alpha is equals to 0 0 vector. These two vectors are equal if and only if the corresponding components are equal. So this can be written as first component of this side is alpha plus beta is equals to the first component of right hand side is 0, and the second one is alpha is equals to 0. So from second equation we get here alpha equals to 0. If we put this value here, so we get here beta is also 0. So we consider this equation, and at the end we got here 0 solution, that is all the scalars are equals to 0. So the given vectors are linearly independent. Given vectors are linearly independent. Now let us consider the another example. Okay, this is our question. Determine whether the set S containing the polynomials 1, x, x square, x raised to n, which is a subset of Pn. Pn is the set of all polynomial of degree less than equal n including 0 polynomial. We know that it is a vector space with the operation addition of polynomial and scalar multiplication of polynomials. So show that this S, check whether S is linearly independent or not. So again we consider here the equation whose left hand side is the linear combination of all these vectors and right hand side is the 0 of the given vector space. So we consider here, suppose the scalars are alpha 1 into first vector plus alpha 2 into second vector, continue, plus alpha n into x raised to n is equals to 0. We know that the 0 of the polynomial function is nothing but the 0 polynomial, 0 plus 0x plus 0x square and continue up to so on actually. These two polynomials are equal. So we know that when two polynomials are equal, if and only if their constant terms, coefficient of x square and so on are equal. So just equating the both sides, constant term and the coefficients of x, we get here alpha 1 equals to 0, alpha 2, this is the constant term, then coefficient of x, in left side the coefficient of x is alpha 2 and here it is again 0 and continue like this. So we will get up to alpha and all the values of alpha are 0. So taking this equation, the system has 0 solution. System has 0 solution means set is linearly independent. So this set is also linearly independent in Pn. Okay, now consider, actually these are the simplest example. Now we consider the another examples. Determine whether the set S is equals to containing these three vectors 1, minus 2, 3, 5, 6, minus 1, 3, 2, 1. It is a subset which is a subset of R3 is linearly independent or not. Again remember we will use the theorem. The theorem says that if S containing V1, V2, Vn vectors and the set S is linearly independent if and only if the equation alpha 1 V1 plus alpha 2 V2 up to alpha n Vn equals to 0 has a trivial solution, that is the values of each variable is equal to 0. So now for that we consider here alpha 1 times first vector 1 minus 2 3 plus alpha 2 times second vector and write alpha 3 times third vector is equals to 0. That is we consider here alpha 1 first vector, alpha 2 second vector, alpha 3 third vector equals to 0. The left hand side contains the linear combination of vectors in S and the right hand side is the 0 vector of the corresponding vector space. So now let us solve this one as usual. So now write the scalar multiplication. So component wise scalar multiplication 1 times alpha 1 minus 2 times alpha 1 comma 3 times alpha 1 plus do the same here 5 times alpha 2, 5 times 6 times alpha 2 minus alpha 2 plus 3 times alpha 3, 2 times alpha 3 and right hand side is 0 vector in R3, which is a 0 set containing all 3 zeros. So now we add all these 3 vectors in left hand side. So component wise addition. So we consider the first component of this addition is nothing but addition of all these 3 components. So first component is alpha 1 plus 5 times alpha 2 plus 3 times alpha 3. Second component is minus 2 times alpha 1 plus 6 times alpha 2 plus 2 times alpha 3. So similarly write the last component. Okay, you can skip this step also after practice. Directly you can write this step from the first one also. So just see how to write this third step from first one by skipping the middle step. So since we want to multiply, do the scalar multiplication, as well as after that we will add all these 3 vectors also. For that 1 times alpha 1 right here plus 5 times alpha 2 and then 3 times alpha 3. This is our first component of left hand side. Next component is minus 2 times alpha 1, this one, 6 times alpha 2 and then 2 times alpha 3. Okay, this second one is complete. Write the last one, 3 times alpha 1 right here, then minus 1 times alpha 2 plus 1 times alpha 3 and equals to the 0 vector of R3. Now these 2 vectors are equal if and only corresponding components are equal. So we equate here corresponding components. So we will get one system. First component here alpha 1 plus 5 times alpha 2 plus 3 times alpha 3 equals to 0. Write the second component, minus 2 times alpha 1 plus 6 times alpha 2 plus 2 times alpha 3 equals to 0. And the last one, 3 times alpha 1 alpha 2 plus alpha 3 equals to 0. So this system is equivalent to the first equation. Now you can observe here, this is a homogeneous system. So you can solve this system either by Gauss elimination method or Gauss Jordan method and find the values of the variables, that is alpha 1, alpha 2, alpha 3. But you can observe here, this system contains 3 equations and 3 variables. So the coefficient matrix is a square matrix, and so we can use the shortcut method also. So for that, we find the determinant of coefficient matrix. So I here write coefficient matrix A. So first row of A is related to first equation, which are the coefficients are alpha 1, alpha 2 and alpha 3. So coefficients are 1, 5, 3. So I write the first row as 1, 5 and 3. Second row is minus 2, 6, 2. Minus 2, 6 and 2, and write the last row similarly, 3, minus 1 and plus 1. Now find this determinant, which is same as by using our regular method. So 1 times determinant of this submatrix, 6 into 1 is 6, minus 2 into minus 1 is minus 2, so it becomes plus 2. Then middle sign is minus here. Then minus 5 times, write the determinant of this submatrix. Minus 2 into 1 is minus 2, minus 3 into 2 is 6, and last is plus 3. Write the determinant of this submatrix. So which is minus 2 into minus 1 is 2 and 6 into 3 is 18, which is minus. So just solve it, which is equals to 8 minus 40 minus it becomes plus 40, and here minus 60, 2 minus is minus 16, which is 48. Okay, so just do this calculation carefully here, which is same as 48 minus 48, that is equals to 0. And since determinant of the coefficient matrix is 0, this says that the system has infinitely many solutions, that is system has non-trivial solution. So this original system has non-trivial solution. System has non-trivial solution, that is it has a solution other than 0. It has a solution other than 0. So S is given set is not linearly independent, that is S is linearly dependent. Now again see this problem, how to solve this problem. Whether we want to check whether set is linearly dependent or independent, so we use the theorem. So this S containing 3 vectors. So we consider the equation alpha 1 times first vector plus alpha 2 times second plus alpha 3 times third equals to 0. Solving this equation, we will get one homogeneous system. This is a homogeneous system. Now we can solve this system either by Gauss elimination or Gauss-Jordan method. But in case if the coefficient matrix is a square matrix, you can use the shortcut method, and that method is in terms of determinant. So here the coefficient matrix is a square matrix, that is number of variables equals to number of equations. So find the determinant of A. A is a coefficient matrix here whose first row is 1, 5, 3, second row minus 2, 6, 2, third row 3, minus 1, minus 1. Just solve this determinant. Since we get determinant equals to 0, indicates that system has non-trivial solution, non-zero solution. If system has non-zero solution, so the set is not linearly independent, and set is not linearly independent means that is linearly dependent. Okay, now just consider the another example which is related to the polynomial function. Okay, so we determine whether the given set is linearly independent or not, or it is linearly dependent or not. So again consider the equation alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equals to 0. Alpha v1, v2, v3 are nothing but these 3 vectors from the given set, and alpha 1, alpha 2, alpha 3 are the scalars. Now put these 3 vectors here. So alpha 1 times first vector 1 minus x, alpha 2 times second vector 5 plus 3x minus 2x square plus alpha 3 times third vector 1 minus 3x, 1 plus 3x minus x square is equals to 0. So you can write directly also, or we can solve left hand side here. So first I have to simplify the bracket. So 1 times alpha 1 minus alpha 1 times x plus 5 times alpha 2, just multiply this alpha 2 inside the bracket. So 5 times alpha 2 plus 3 times alpha 2 x. Next term is minus 2 alpha 2 x square plus alpha 3 plus 3 times alpha 3 x minus alpha 3 x square is equals to 0. Now if the vector space is a polynomial space, so for that here we collect the constant terms, we collect the coefficient of x or terms of x and x square. So we rewrite this equation. So first I underline the constant term. So these are the constant terms, I put these 3 terms in one bracket. Okay, next double underline the terms of x. Okay, these are the 3 terms, and from these 3 terms we write in one bracket or simultaneously we take x as a common. So minus alpha 1 is here, coefficient of x. Here coefficient of x is plus 3 alpha 2, and for last it is 3 alpha 3 into x. And similarly the last term we take together and take x square as a common. So there are only 2 terms of x square. This is the first one and the last one. Is equals to 0. The right hand side is 0, nothing but 0 plus 0x plus 0x square. It is a polynomial whose all coefficients are 0. So just equating both the polynomials here or polynomials on both sides. So first we equate the constant term. So here constant term is, and the right hand side the constant term is 0. Then equate the coefficient of x. So in left hand side the coefficient of x is minus alpha 1 plus 3 times alpha 2 plus 3 times alpha 3 equals to, this is equals to coefficient of x in right hand side, which is again 0, and do the same thing for the last coefficient. So this is our system. So remember, all these systems, all these equations are same here, or this system is equivalent to the first equation. Now again here you can observe here, you can solve this system either Gauss elimination, Gauss-Jordan method. Here there are 3 variables and 3 equations, so you can use the shortcut method. So for that, calculate the determinant of coefficient method, coefficient matrix. So first row is coefficients are 1, 5, 1. In second row write these coefficients minus 1, 3, 3 again. And here alpha 1 term is absent, so corresponding coefficient is 0. Next are minus 2 and minus 1. Now solve this determinant. Minus 3 plus 6 is 3 here, so write just 3, it is minus 5, it is 2, okay, again it is answer is 0. Answer is 0. So system has infinitely, system has, if this determinant is 0, system has non-trivial solution. System has non-trivial solution indicates that the given set is linearly dependent, that is, which is not independent, so it is a linearly dependent. And remember one case, suppose we get determinant equals to not equals to 0. So in that case system has trivial solution. Trivial solution means all variables are equals to 0. and so given set is linearly independent. But remember, in this case, since we get determinant is 0, so this homogeneous system has non-trivial solution, that is solution other than 0 exists, and so given set is linearly dependent, that is it is not linearly independent, or vectors are not linearly independent, so they are linearly dependent. So take one example of homework and check whether the set this is a set of R3, check whether it is linearly independent or not. Okay. So this is a very important topic of linear algebra. And remember how to check whether the set is linearly dependent or independent, because it is useful for solving the problem of basis also. Now let us recall the previous recall the lecture first. In today's lecture we have studied definition of linearly dependent or independent, related theorem and the examples. So if V is a vector space and S is a subset of V, this is said to be linearly independent if no vector in S can be expressed as linear combination of other vectors in S. If S is not linearly independent, then S is said to be linearly dependent. S is said to be linearly dependent. So now there is one theorem related to it, and theorem says that V is a vector space, S is a subset of V. This set is linearly independent if and only if this equation has trivial solution. Trivial solution means zero solution also here. And remember what is meant by zero solution? Zero solution means alpha 1 is 0, alpha 2 is 0 and alpha n is 0. So again see the theorem, S is linearly independent if and only if this equation has trivial solution, zero solution, or this one. Another way it's we can say that if S is not linearly independent, that is S is linearly dependent if and only if this equation has non-trivial solution, non-zero solution, or you can say that infinitely many solutions also. That is, there exists at least one solution among which at least one variable should be non-zero. And also remember one important results while solving the problem. So if I consider a non-homogeneous system, homogeneous system Ax equals to 0, this system has zero solution, that is also called trivial solution, if and only if determinant of A is not equals to 0. And the same next result is this system has non-zero solution if and only if determinant of A is equals to 0. In case of solving the problems, you can use these two results. Okay, today we stop here. Next lecture we are going to study the another topic which is related to how to check the linear independence of the function by using Wronskian. Thank you.